sitting here talking to myself. All right, I'm sitting here talking to myself, not realizing that there's no audio. How does the font look for the chat? That looks okay to me. Um, I'm going to minimize this. Hopefully the stream is okay. We'll do our best with what we've got here. I'm streaming cellular data plan, which should be okay. Hopefully the screen is visible. All right. Let's see if I'm seeing any chat. I see 2 viewers. Let's see who's in here. Orab and Scald. Hey guys, how's it going? Let me know if you can hear me. Okay, and if you can see things. I'll explain what I'm doing with this all shortly. Just give me a moment to kind of get myself situated here. I clearly skipped some steps that I needed. Is that not what I thought it was? Yeah. Where's my downloads? What is the path of users? Downloads. Let's see. Okay, good. So you can hear it and see it. Great. Okay. Let's see. So we need to add here vbcc bin and users downloads vb link. And users Michael downloads via ASM. And then export vbcc is to users Michael downloads vbcc. I think I got that all. Great. So downloads, no. Development, BC, oh shit, plus NROM 256 vertical, with the library laziness, and output, yes. All right, cool. So that compiled. All right, great. So I was just setting up the compiler here so that we could get everything going and make sure that we have the right libraries available in the header files in the Portland Convention Center now here. We just got our badges for the Retro Gaming Expo a little bit ago. So this year it is Pac-Man themed. Pretty cool. All right, so the plan here is, I don't know that I'm going to stream literally as much as I can. I figure we'll kind of see how we go here, how much I can make on this one charge of my headset, and see where that takes us. But, you know, part of this is I'm going to start streaming development of the shooter again, so that we can kind of get that game worked through and completed soon-ish, maybe. But just getting back into streaming and trying to do something fun here while I'm at the Retro Gaming Expo, to kick that off again. So as part of that, we're investigating essentially like what it looks like to work with the C compiler. So I had initially looked at working with CC65 just because that's the one that I knew, because I'm using CA65 for the assembly. But it seems like Memblers was saying that the compiler on vbcc 6502 is better at generating code. It has an optimizer built into it, so like when I run this compilation, I can say O2 to optimize the code, and it will go through and try and generate more optimized assembly code. And apparently, it does a pretty good job. So we'll see how that kind of goes later on. I'm not super concerned about that right now because we're just putting together a basic concept here using the C code, and we want to see how that all fits together. All right. So any questions on any of that stuff before I get started? And I'm pretty sure Twitch is recording this. It should be recording this, so hopefully we'll be able to play this back and see if this was a success or a disaster.
But I got one of these. Yeah, I don't know if there's any others open.
All right, so
Any other restaurants or anything?
all right, I don't see any comments from anybody or anything, so let's get started. All right, so the main thing is we're going to be using this header, this lazy NES header that has some basic functionality built into it to make our lives easier. You can access the hardware directly still. If you look at this, open this file here, there is a basic header file that comes with vbcc that is kind of just to define some simple macros for the memory addresses for the different registers that you can access. But the thing with laziness is it gives you some ability to do some cool things that are a little bit simpler when accessing things like the PPU memory. I was messing around with this, so I'm going to be referring to this code a little bit so that we can kind of bypass some of the learning that I had to do before I was ready for the stream. So, if we take a look at this, we have the ability to define just raw data, similar to what we can do in assembly, where we just write out the different bytes that we're using. The only difference is that, you know, this is going to get assembled separately from the C code that we're compiling. So I'm going to essentially use what we have here. I'll explain each section in a minute, but I'm going to use the same code here just to have us be able to define some of the basic data we need and have our palette set up correctly. So this section, similar to what we have in CA65, where we define, if we go to go to the Hello Mario example for a second that I put out there. Um, Come on. Yeah. Unfortunately, I don't know how good the internet connection is going to remain here, but we'll do our best. So if we look at the assembly code here for this example, you can see we have these segments that we define, and those segments are tied to configuration that CA65 uses to know which portion of the what specifically you're referring to. So like the header is only useful for emulators, obviously. These segments, like you have a zero page segment for the zero page memory, and then you have the startup segment, which is where the ROM actually begins, the code ROM. So similarly, we have a section definition like this: read-only data, the ROM data, and then what we're doing is we're defining this thing called palette data, which is just raw palette values that we're going to want to load into memory. So I'm just going to copy and paste this. Now, just having this as a file is not enough, and just even assembling this along with the other code. So what I'm doing is I'm compiling the C file. I'm using this configuration file that has already been predefined. It's for an NROM 256 with vertical mirroring. I'm saying I'm including this laziness library, which we have the source for if we ever want to take a look at it. And then I want this NES file as output. So I'm going to include this ship.s assembly code. Now you can see I made a mistake. I did not copy over the section data, which is why it's complaining. All right, cool. So now it stopped complaining. So now that data is just compiled in raw into the ROM, but we need to be able to access it somehow. So if you've ever worked in C, there's the concept of an extern. An extern is just saying that it's something that you're referencing that comes from another file or another library that you're compiling or accessing against. So like if you have multiple C files, you might in one file define a global variable or some sort of global object that you want to have access to in another one, and so you declare it in a header or in this case in the source file, but you don't want to create it as an actual variable. Like if I say it's a constant unsigned character called palette, and it's an array, and then I go to compile this, I think I'm going to get an error probably. Yeah, so this is saying it's incomplete. I could say, okay, well then, let me give it some sort of data. And that seems to work, but it's obviously not referencing, you know what? Called it palette data. Let's see if this gives me an error. Yeah, all right, so there we go. So that's what I was expecting it, and it helps if I use the right variable name, and it'll give the error that you expect. So it says global symbol palette data from this. It's already defined in this. The error message is kind of crappy, and it doesn't explain what the problem is. But basically, I've defined this thing here that already exists in this, right? So that's what the problem is. It's just saying you can't do that because there's already something called that. So the solution is you say, this is an extern, which means that it knows, like, you can use it and work with it however you want. It's expecting to see the actual definition of it in some other file or library. So when we go to recompile it here now it stops complaining. And if we wanted to, I can even say palette data. I can reference it in the code. I'm not doing anything to it, obviously, right now. Obviously, that has no effect, just putting it with a semicolon, but has the effect of, the compiler is actually trying to resolve it. So if it didn't exist, it would give an error. If we do this. So I'm explaining all this stuff with the C code in a little bit more detail than I might normally because we haven't been doing any of this stuff. We've been doing the assembly straight up. So it's a little bit different. So you can see it's like, I don't know what this is from what I ever found. Unknown identifier. So the CERN is important to make sure that it finds this thing, and you got to make sure you make note of the fact that it has an underscore there. That's part of how the assembly and linking goes for the naming convention. So there's no underscore here, but when it gets assembled, it's looking for it with an underscore in the code. Anyway, so nothing actually happening so far. At least that's what it looks like. But if you go and you look at the code in the disassembler, so I have FCEUX loaded up here. If you go to the debugger and you go to the address, since this is NROM, we're starting at 8,000 for our ROM, and you can double check that by looking at the vector table that says, where we're starting. If we go to enter the address, 8,000. Okay, so you can see we do an SEI and a CLD, and that should look familiar because you go to the Hello Mario code. It's exactly what we're doing in the beginning of our code. Like, that's our boilerplate code for the assembly that we normally do when we're starting up our game. And that's all coming from, there's some boilerplate code that comes from vbcc and LazyNest to define, like, this is how you initialize your system before you get started, and it actually calls the main application. If you look, very similar to how we're clearing out the memory here, there's a loop further here. That, again, looks familiar, right? We're transferring the X register to A, and then we're storing into 0, 100, 200, 300, 400. Right? We're just iterating through all the RAM, and we're initializing all the RAM to make sure that there's no random data in the RAM when the game starts. Same concept as what we've been doing in the assembly code every time we start. So the nice thing is this takes care of that for you. You don't have to actually do anything to make that work. So the question is, okay, how do we do anything with this? Like I said before, you do have access directly to the registers just like you would in the assembly code, because you have access to the raw pointers by, saying it's a volatile pointer. Volatile is important because if you're using an optimizing compiler with hardware, I learned this the hard way when I was doing Game Boy Advance programming. So if you don't specify that it's a volatile pointer, the compiler, trying to be helpful, will say, okay, you're reading from address 2000, but I know you haven't actually written anything to address 2000. So when I read it, if I've already read it and I have the value cached in memory somewhere already, there should be no change. But the thing that it doesn't know is that 2000 in RAM is not just RAM, it's actually directly accessing a PPU register, right? So doing that read or write, you want it to always actually go to the RAM rather than optimizing out that request, right? It might completely skip generating the code to read that because it says, well, nothing changed. So there's no point in actually reading it, trying to be helpful and optimize your code and remove instructions that are unnecessary. But in this case, we want it to always read, because if you don't, then you're going to get weird results because you don't actually check the hardware to see what happens. So that volatile keyword, very important to tell the compiler, basically, like, yeah, I know you're trying to be helpful, but please don't, because I know that it's possibly going to change even if I haven't done anything to it. Like, that's especially important on these control ports where it's user input on the controller. We don't want it to assume that nothing happened because we didn't do anything to it, because the controller is an external device hooked up to the system, and so it could change based on user input. The challenge with that, though, is because you're working in C, your code is not necessarily as streamlined as it is in assembly. You're not getting one-for-one necessarily. We can actually look at the raw assembly code that gets generated here. Where is this? Let's close that. So one of the nice things that this vbcc has is it has the ability to turn your C code into assembly directly so you can see what it looks like. I just need to make sure that I am including the right include files so that it knows how to resolve that stuff.
But I see a lot of people like her.
The same thing I've been doing every time I try and do this. So there's no space here. I have not BI set. All right, so now you can see there is a .asm file here that just got generated. And if we take a look at it, this is the assembly code that got generated from our C code. Not much is happening, but we have our main function here. If we were to do something like, say, int x equals palette data 0, and regenerate this, you'll see that now it added some new code, right? So it manipulates the stack a little bit to, let's see, subtract carry, store it into the stack pointer, rent carry, set to 16, recommend stack pointer plus 1. Okay, so it's doing a 16-bit operation on the stack pointer, it looks like. So then it's loading with the palette data value, it's loading, with the, is it the address of palette data maybe? Looks like it, yeah. So it's loading the address of palette data into A. I guess it's a 0-page register. Oh, wait a minute, it's doing that for the stack pointer. Oh, I guess because it's the 0 index, it can just load the first value. Let's make this a little more interesting. Let's go to position 1. Let's see what it does with that code. So it's, it's just incrementing the pointer, literally doing 1 plus. Interesting. So if we did something like, what would it do here? Let's see. See, okay, so here it's loading, it's transferring. Very interesting. So it's in this case, it's loading the high value and low value of palette data as a 16-bit value into the stack pointer. It looks like, which is our variable, right? Like these variables are all in the stack. They're not just directly registers like we normally deal with, and it uses the stack more so than we do in assembly, where we're generally just referring to specific RAM locations. Like if you think about what we've done in Cerulean Ascension, where we're referencing specific values in our memory, they're not stack based. The stack is just being basically used for when we do subroutine jumps and some other things, and we're generally not using the stack for storing any of our variables. But this is pretty common for C compiler, where it's going to use the stack in order to have variables. Now, part of that can be a little bit slow. If we wanted to make this a little bit faster, we could say, int x is here, and then we can reference it like this. And obviously this has nothing to do with the game. I'm just kind of showing you this because I thought it was very interesting, related to how the compiler is actually working. And so what happens is now we have this global X that's in the code, and that simplifies things greatly because it's now just in the RAM directly. It's not on the stack, because main is a subroutine, just like any other subroutine. You can notice that we're doing a return from the subroutine here, RTS. That's just like when we do any of our other subroutine returns. Uh, so this isn't really a special function compared to any of our other things. And normally when you're calling a function in C on any platform, you're dealing with your local variables being on the stack. So that's exactly what it's doing in the case that we were looking at here. But if we move this out to be a global, then it doesn't need to do that because it exists for the lifetime of the application. And that's an old trick that they used to, old games on DOS, for example, and back in the 80s and 90s. That was like a easy trick to optimize things like anything that you would reference often, or use in like a tight loop or something where you needed to optimize your runtime a little bit. It's easy to just get a little bit of performance by moving things out into the global space, so that you didn't have to worry about stack allocations and working in the stack. Um, Obviously, nobody does this anymore because global pointers are considered like evil and bad. But from a performance perspective, they're definitely optimal, especially on a CPU like the 6502, where you don't have a lot of registers to kind of juggle around things like you do on the x86 or a RISC processor, and and so you're working with the stack almost always, unless there's some sort of optimization that the compiler can see, um, with whatever operation you're doing. So anyway, so my point going into all of that is we have the ability to do direct access to the hardware, not necessarily optimal for the C code because it generates a lot of additional stuff that you might not be aware of, like all those stack accesses. So for simple stuff, we might do this, but the laziness library has some nice functionality that we can take advantage of that will help simplify some things. So one of those things is it has the ability to wait for v blank to occur. I just want to double check this because there was some weirdness that I couldn't remember. Yeah, so there's this ln sync. It's just a way of telling the code to wait for v blank to occur. Um, this is for things like it says with sprite 0 and any other kind of weights that we might do. We're not going to be dealing with any of that here, so we're not going to touch that for now. But just like with our assembly code in here, where we want to wait for v blank a couple times before we actually get started, you can see we do a wait here, just as an initial wait for the system, and then we clear out our memory and we wait for another v blank here. We're going to do the same thing where we're going to wait. I still don't remember all of these flags because it's a little bit new. So we're gonna do a double wait here, right? So we look at what that looks like. Nothing crazy here. We're just calling a jump subroutine, right? Where A is being used as our parameter to call this method, and then we're just doing a jump subroutine. It then takes the value of A and stores it into a free register in case there's some sort of return value that we would be getting from calling the subroutine. In this case, I don't know that there is. Okay, so it's using the ubyte return result amount of frames since last sync. Okay, so it's giving you some information back if you actually needed to know how many frames passed between when you called it and when the last sync occurred. All right, so we're going to wait there. By doing that wait, we know the PPU will be ready for receiving data. So let's load up the palette data that we are supposed to be loading up here from this. So it has a method called push. And this allows us to load into memory addresses from other memory addresses. Specifically, it's for PPU. So what we want to do is know the palette memory starts at OX3F00. So we're going to say on push, and we're going to use that address as our starting point. We're going to say there are 32 bytes of data because there are 4 background palettes, 4 sprite palettes, each with 4 bytes apiece. So that's 16 for sprites and 16 for backgrounds, 32 bytes. Palette data is what we're actually pushing into there. So let's actually compile that so that we can look at what we just did in the emulator. So thankfully that compiled with no problem. All right, and you can see we already got to change the background change to that blue color. And if we look at the PPU viewer, we've got palette data loaded up. Whereas before, we didn't look at this, but if I take this out, recompile the code, and reopen it, we have the black screen, which is the most obvious difference that we notice. But you can see the palette data is completely zeroed out. So that's just as a result of doing the ln push. And ln push is, as you can imagine, it's just the same. Again, the same code that we wrote in this code here, where we're syncing up the palette data from here. So we have this read-only memory that we're defining here in the assembly code called palette data, and in this case, we're where is that? So in this case, we're setting the address of 3F00 by setting that, writing the 2 bytes to 2006, which is the PPU address register. And then we're initializing our X register, and we're just counting to make sure that we are writing 32 bytes of data. It's the same basic principle, but again, a little bit more straightforward in the C code versus the assembly code. All right, so now that we have our palette data loaded, let's talk about, let's see, we're going to need to access the controller, and it has this this method for reading controller 1 or 2. And what it's gonna do is it's just gonna pack a byte with the different bits that could be set based on what is pressed. So this is similar to what we had done in our code where we were looping through, and because remember, the NES controller, when you tell it that you're interested in the input, it's taking a snapshot of the state of the controller at that point in time, and then you're essentially shifting all 8 of the controller button states off the controller and into the CPU. And so each time you read from the controller, you're getting one more bit of data that tells you what was pressed. So first, you're potentially getting the right button, left button, down, up. Where's the order? Select, start, B, A. And when we read the controller data off of the controller register, what we were doing is we were just packing all of those individual bits into one byte so that it was easier to work with. We could use bitwise operators to compare the content of that byte and then see what we should do. Like if they press start, we should pause the game. If they press A or B, we should perform an action. So this takes care of that functionality in the same way that we were doing it, but just with a single call. So we'll definitely want that here. And what we're going to do is we're just going to have a loop where we read now. So this is a case where I'm putting it in the global space because there's really no point in No point in having it be a local variable for me, because we might need to access it somewhere else potentially, but also we're going to be reading and writing to it very frequently in this loop, and it's just totally inefficient for to leave it in there and then have it be in the stack. Um, so, I say it is. So we're just reading controller one. And then the last thing we need to do is in our while loop, again, similar to what we're doing with Cerulean Ascension, is like after we've processed all the game logic, we need to wait for NMI to run and complete, in order to make sure that we're actually ready to process the next frame of the game, right? If we try and do everything in real time with the CPU versus what happens on the NMI, we're going to get ahead of what's actually been rendered. Because if we go to the assembly code, this is a very, very basic example, but like in the NMI code here in Hello Mario, we are just resetting the sprite data so that we make sure all of our sprites always get rendered properly, right? If you don't do that, then the sprites disappear because of the whole dynamic memory thing. So we need to be doing that on the NMI, but at the same time, in our game loop, we don't want to start processing more frames than we've actually rendered, because then we're going to see the sprite jumping across the screen, right? Because this loop might run 100 times before the NMI actually runs. So we got to sync these up. And so what we had done in Cerulean Ascension is we just had a loop inside of here that said, okay, wait for the NMI code interrupt to finish before we then process the next loop. And that synchronizes this code and the interrupt to ensure that they're in lockstep and we're only processing the game logic once per frame. So similarly, we have the ability to do that with ln-sync. You do an ln-sync with 0, and that just waits for the NMI to complete. So now we're only checking the gamepad state once per frame, and we'll be processing whatever other logic we have once per frame as well. So let's I'm singed, I'm signed. So nothing super exciting happening yet because we're just basically going through this whole setup process. One thing we should probably do is we should probably turn on the ability to render sprites and backgrounds. I'm going to just steal this code here from what I was working on before, and we'll talk about it in a second. Why we're doing this and what it means. So I will point out, so LNPPU control and LNPPU mask, these are, the laziness library has these variables defined for what you want to set these PPU registers to during the NMI code, right? Because you don't want to change these values. You don't want to change these values in the middle of a frame rendering. Right? You need to wait till the frame is done rendering before you change anything that would control, like whether sprites are rendered or the background is rendered. Otherwise, you're going to see tearing as half the page is drawn one way and half the page is drawn another way. So we want to set that value through these LNPPU control and LNPPU mask variables, and then that means that the laziness library in its NMI code will actually update the registers for us in that way. So all we're doing now is we're saying, okay, I want to tell the PPU to use background table 1. And what that means is if we go back to the emulator, although there's no difference right now, there's this pattern table 0 and pattern table 1. And what we want is the background to use pattern table 1, and we want the sprites to use pattern table 0. So we set that through this, and then we tell it also, yes, please generate an NMI interrupt, the non-maskable interrupt. And then we also say, show the background, show the sprites, and also show leftmost sprites. And these are all just constants. If you go to the NestDev wiki, you can see that these are all the standard values, all the standard registers. There's nothing special or different from how we would do this in assembly other than, like I said, we're putting it into a variable for the laziness library to set for us, whereas in the assembly code, we're responsible for doing that all on our own because we're writing the interrupt handler to handle all of that. And similarly, there are variables for the scrolling. We'll play around with that too so you can see how scrolling works with the background. All right, so we've got that stuff set and enabled, and so what we should see is when we build this, there should be like some random sprite stuff on screen now. Maybe? Oh, well, there won't be because we don't have a real, we don't have any real character data. I forgot about that. So let's go grab the character data from Hello Mario. We're just gonna steal this and then we'll edit it to work with what we're working on right now. So in the assembly code, we do an include bin, right? Include bin to bring in just a file raw without any processing. It's not code. We're not trying to assemble or compile it. You can do the same thing here. We just have to be careful that we're telling the assembler what section it lives in. And similar to the assembly code in CA65, that's done by declaring this section chars. And we're going to ink bin. I don't know if the spacing actually matters. Let's see. No, it looks like it's okay. So if we run this, let's see, did I mess something up? Oh, no, okay, so we have our character data now. If we look at the sprites, oh, you know what? It's chopped off because the emulator is probably cropping. Let's turn off cropping. That's weird. It should have done it. Oh, what am I saying? We're not setting the sprites to anything right now. Okay, I'm getting ahead of myself because I didn't think about that. So, all right, so that's basically where we're at now. If we look at the code that this generates, again, it's like familiar, right? We're going to be doing the same thing that we're doing in all the assembly code that we've been working on from the very beginning. So the only kind of interesting thing to point out is like it's loading the aggressive palette data into some locations to be able to call this ln push, right? Which is storing our palette data. We're doing this call to set the LNPP control and mask, like we talked about with these values. This is just the decimal value of the hex equivalent of what we're setting here by doing the bitwise operations. I decided to make these macros. I forgot to talk about this before. I did the macros just to kind of make it more C styled. You know, we're not just putting random hard-coded hex values. It's a little more readable this way. And then we're just calling the get pad, right? It loads A into get pad. It stores the value of A, which is the return from get pad, into, right now it's saying registers, register 0. I guess that's probably meant for an optimization. Like if we were to have to use that right away, it would be in some register for us to use. Keep in mind, this form of the assembly that it's generating here is not the final assembly. It uses some temporary placeholders uh, based on, I think, some of the optimization it does downstream before it creates the binary, and we'll put in whatever register actually makes sense. Again, that's a pretty common thing for an optimizing compiler to do in order to kind of give it some wiggle room where it says, okay, I'm going to use a register here. I don't know what register it's going to be based on. The fact that I don't know what kind of optimizations I'm going to do later on down the road. So maybe it's going to be A, maybe it's going to be X, maybe it's going to be Y. We'll see. With the 6502 not having that many registers, um, I suppose it's possible that it might actually even store it in RAM somewhere. But anyway, and then it does store it into this buttons variable that we defined. If you look here, it's just this single byte that we've put a value of 0 into to initialize it. And then it loads it calls the sync call, and then it jumps back to L3, which is the loop that we created in this infinite while loop. So, all right. So now that we have all that stuff, all the stuff we've been doing here is essentially the same. Dealing with the sprites is a little bit interesting because, so much of that is about setting up memory for sprite use, because we have to copy it all from RAM to the PPU for the dynamic RAM that the PPU uses in order to constantly update the sprite data for display. So this uses a format, I think it said it's similar to the format that Shira uses for his C libraries for the NES. And basically what that is let's take a look at this. I believe it's X, Y, yeah, it's X offset, Y offset, the tile that you want, and then what the attribute value is, like what the palette is. Oh yeah, it says it's the same format as OEM Metasprite from Shiro. Now this is actually kind of interesting because it gives you some flexibility when rendering sprites, because it almost works like how a 3D model works, where you have local space and then you have global space. So when you're defining your sprite to pass to it, you're defining all the sprites with offsets that are local. So let's say you have a two sprite by two sprite object that you want to define. Have any way of drawing this? No. Well, so it's like it's two sprites by two sprites here. So normally, what you have to do in your code is you say, okay, this sprite is at the because all the sprites are almost always defined by the top left corner XY coordinate. So this is at that XY coordinate. This sprite is 8 pixels to the right of this one here. This one is at the same X coordinate, but it's the Y coordinate is incremented by 8 to offset it from the top left corner. And then this final sprite is both the X and the Y are incremented by 8 in order to have it be in that bottom right corner. With this, you don't have to do that because it is allowing you to say just simply like, what is the offset from the top left corner that you want for drawing the sprite? So you just work within this local space of some simple offsets, and then when it comes time to draw the sprite, based on where it is on the screen, you tell it like this is the XY coordinate on the screen, and then it uses the offsets to figure out where the sprites actually need to live. So it's a convenient way of handling that sort of sprite drawing. So let's put together a quick example here of how that looks like, or what that looks like, I should say. So I'm going to do that in this assembly code just because it's a little bit easier to define out just the raw values. So the actual sprite values don't matter right now. We're just doing this to get something on the screen for now. So we've got the X and Y offset for the top left corner are both 0. Let's say it's tile 0 with attribute 0. It's just the base palette, right? And then the second sprite is going to be to the right of the first sprite. So we want to increment the X value by 8, leave the Y value alone. It's the second tile, so 0, 1, and then the same thing as before with the attribute. And we're going to do that 2 more times, and just kind of like what I was saying when I was typing it out. We're going to then increment the Y by itself, and then we're incrementing the Y and the X, and we just want to increment these tiles so that we get different tiles. So now we have this ship sprite constant that we can use in our code here. So just like with the palette data, we're going to define this as an extern so that it knows it needs to look for it somewhere. And then unlike what we do in our assembly, so in our assembly code, if we go back to the Hello Mario example, we have the sprite data defined here. These are just the raw values that need to go into the OEM data as defined. Here, right? So there are these 4 bytes. There's the Y position, the index number with a bank bit. So the index is offset by 1 bit, and then there's this base bit that tells you which bank of sprite tiles you're looking at. Then there's the attributes. These values are going to be the same in our assembly code here as they are in the documentation. So if we wanted to do something like flip the sprite vertically, we would want to set bit number 8 in order to make that happen. In this case, we're not doing any of that stuff. We're just setting everything to 0 because it doesn't matter. And then the last byte here is the X value, which is the same thing as the X value that we have over here. So by defining that, we have now the ability to say, okay, this is our ship sprite. Now, the other important thing that you need to do is you need to identify that this is the end of the sprite definition using the 128 value, which is just a setting the bit number 8 or bit number 7, whichever you prefer, the highest bit to 1. So now that that's set, we have the ability to essentially queue up the sprites that we want to draw on the screen. So there is, what is that called? Oh, add sprite. So here's what I was talking about. So we have the ability to say, I'm going to add sprite, and we're going to add our pointer to the sprite data, which is ship sprite. And then we have an X and Y offset. So this is like if the ship is in the middle of the screen, for example, we can just say here 100, 100. It's not exact center, it doesn't matter. The point is that we'll see a sprite show up somewhere in the middle of the screen. So let's go back to this and compile. And there, because of the way that the emulator is squashed, it's changing the proportion. But there's part of Mario's head because we're just still using that same generic character file for our sprite data. All right. So let's do something a little bit interesting with this. Let's like actually try to have this move around based on input. So let's create a struct called player. I don't know if this is actually going to be correct or not for what we want to do, but like we're just kind of building this in real time. So if we have to change it, we'll just change it. So we have this player type. Um, so the nice thing about this is like you have all this ability to structure your data a little bit more cleanly, like you would in a normal C program, which is a little bit harder to do in assembly because it's so much more low level. It really requires you to kind of understand that, like the concept of a struct in assembly is really just like semantic sugar, essentially, where you're just kind of having it do some basic math for you so you don't have to, and you're putting a name to it, but it's very, very basic. It's very, very low level. Here, we can actually refer to it as a real struct, and it should work pretty nicely. So what we can do is we can say, okay, if buttons, well, let's do it this way. If 0 is not equal to buttons, and what is the definition that was done here for this? It's LFU. So basically, we're saying, let's do a logical and against buttons with the laziness flag for up, and if it's not 0, that means that controller button was set. And what we want to do is we want to subtract from player.y. And kind of on the flip side, if down is set, let's add to player y. There we go. All right, so we can move Mario up and down by just pressing up and down on the keyboard. And you can see it's actually relatively slow, but it's because it's locked in step with the frame. So it's only moving 1 pixel per frame, which is like a comfortable move speed for what we're doing right now. Similarly, we want to do, I'll make this as an else if, because like I don't want it to be that if you're pressing up and down somehow, like you have a really shitty controller or something, that it's going to allow you to do that. So same thing if we're pressing left, it's going to change the x coordinate by subtracting. And if you're moving right, it's going to add. So now I can move Mario all around. So we have some basic movement here. So I'm going to pause for a second. I'm going to take a little bit of water. I'm not sure how long of a stream I'm going to be able to do, like how long my voice is going to hold out for this. But I wanted to ask for those of you who are on this, how has the audio been? How's the video been? Because like I said, I'm streaming through my phone, and I am also streaming on my Mac, which I've not done. So everything okay? I haven't seen any comments in the chat. I see some of you guys are here. Some of you people are here. So let me know how it's going. If everything is looking good and you can hear me and understand me okay. I also don't know how much longer my AirPods are at 75%, so they should last a decent while still. If it lost 25% over an hour, we could definitely get at least another hour or two out of them. So what I want to do next is I want to change the sprite data to not be Mario's head and be something actually appropriate to what we're working on. No takers. Nobody wants to tell me if the stream is looking and working okay. See Mirror Loop on there. Brendan 812, how's it going? Glad you were able to make it. Well, let's start by messing around with this sprite data. Then I'm gonna take silence for everything is working okay. Unless I've been talking this whole time and nobody can hear me. I mean, I'm seeing the audio levels in here, so I'm pretty sure you guys can hear me. But let's go to the folder where that character file lives. All right. So nothing has changed there. For real, I'm just double checking. Is audio and video okay? I'm an hour into this and nobody said anything, so I'm going to assume that everything is fine. Which I'm kind of surprised about. I thought streaming off my phone would not work, but it seems okay. Except my leg fell asleep sitting here in the convention center. All right. So here are the four sprite tiles that we're working with right now. What I want to do is I want to clear them out. I'm actually using Wine to run YYCHR on the Mac. Seems like it's working pretty good, just because YYCHR is a really nice tool, and it, I don't know, I know Tile Molester technically works on the Mac. I just don't really like using it. All right, so let's clear out this these tiles here, make them empty. What we'll do is we know what the palette looks like, so we can kind of choose colors that actually make sense. I should be just flood fill. Okay, cool. Flood fill these colors out. So can I do this? Yeah, there we go. Oh, it's on a fill. It's just that was an outline. Okay, cool. So now what we need to do is we need to choose that brown color and kind of make a basic shape that I want the ship to look like. And in this case, in this context, a ship meaning like a boat. All right, so let's see if we can do just a basic kind of boat shape. Clearly, I am not an artist, so for anybody watching this who has any sort of art sensibility, I apologize ahead of time. I am not good when it comes to this stuff. All right, so save that. I should be able to now update the ROM to FCEUX crashed on me. Let's recompile that, and we should see now that Mario is not there anymore. It's this dumb little sprite that I made. Alright, so now we have that going. Ideally what I want to be able to do is actually have this rotate in a number of directions. I'm debating if I want to do that in something like... Can I do that in a sprite, I wonder? I'm not sure. I mean, I know I can rotate things in Sprite, but I'm not sure if I'm going to be able to. I'm going to be able to do it in a way that I can then map it over back to YYCHR. Let's see. I just copy this. Can I paste this into here? I don't know if, because this is in wine, I'm not sure if it will allow me to do clipboard stuff like you might be able to do in normal applications. It looks like no. But I also don't know if that's a limitation of YYCHR in general. Hmm. We missed the row and more people wandering over. So these people here who don't seem to see that I'm doing something and they're just standing there and taking pictures. Anyway, let's see what we can do. I think there's an NES palette already built into a Sprite. If I can just find where that is. I thought it was just built in. Let's see, default palette. All right. I don't know that really matters for what we're doing right now. I can always come back and build a different Sprite later. So, yeah. So, part of what I want to do here was make some code that just kind of followed the sprite around and worked with the scrolling registers. I want to keep it really simple where we're not doing any sort of dynamic name table loading. I just want it to be really, really simple so that we don't have to worry about like the complexities of loading the name table dynamically. And this is vertical mirroring, so that means we have space along the horizontal name table right now. So we should be able to kind of work within that. So the concept of what I'm trying to put together here is like if you've ever played Lunar Lander, so in Lunar Lander you have your Lunar Lander in space and it has a certain amount of fuel and you can increase and decrease the thrust while rotating the lander. The idea is there are sections in the moon that you want to land the lander on, and depending on where you land it, it's for double, triple, quadruple points, right? And so similarly, I was thinking it'd be kind of cool or fun to have a concept where you have a boat, and I'm not sure how complex. There was part of me I was thinking, well, it'd be cool to do like you literally leave one port and you navigate through different obstacles along the way, and then you have to dock the boat again, all without running out of fuel or crashing into things. But I also don't want to make it overly complicated and not finish it. So I wanted to focus on, at least for now, just like can we just do the initial, like it brings you into it at a point where you're going to dock, and so it's like the final approach, and you have only a limited amount of fuel to do it, and there's going to be wind that offsets the motor pushing the boat, and there could even be current where the current of the water is also dragging the boat in another way. So let's, I don't like how kind of like fat that sprite looks. I'm going to trim that down a little bit, and then we'll start implementing some of these basic kind of gameplay things. So I'm just going to make this a little bit more narrow. Not critical, but it just kind of looks weird, and I don't like it. All right, so let's save. So I should be able to rebuild this, and I shouldn't do that. All right, let's see. So yeah, that looks a little bit better. Okay. Like I said, I want to make this so that it actually rotates as you rotate the ship, and I don't know how many degrees of rotation I would support, because unlike in modern games where you have the ability to do just kind of free rotation with whatever level of support that you want, and there's sort of no penalty because it's just a 3D object that you're rotating in the in the space. This has to all be kind of pre-drawn. So then however many degrees of freedom I want to have, I have to have a pre-rendered sprite to make that work. So um, let's leave that for later, because I don't feel like messing with generating different sprites. So I'm just making sure that the video and everything are still working. So, all right, that's the first thing we want to do. So let's populate the name tables with some data, just so that we can see the play field that we're dealing with, and then I want to move the sprite and have that offset the name table a bit, and then and scroll the PPU a little bit. So we're going to kind of do this the lazy way just for now. I'm not going to go through like creating compressed data for this. It's just going to be some basic data here for us. And I really don't know why these people have to do this here while I'm purely sitting here and talking to everybody. So they just continue to be here. Let's, I do still have this running. So let's look at the CPU viewer, and let's see what tile would be appropriate. So like tile 25 for the name table is good. So what I want to do is just kind of define the boundaries of the name table, which let me refresh my memory on, I think it's 32 by 30 tiles. I feel embarrassed that I don't remember, but it's been a while. It's 1024 with 30 by 32. Okay, so 32 by 30. Like I said, I'm just going to do this really, really basic. We're just going to populate the bounds of the screen. So this is what we got: 8 here, 16, 32, 64. All right, so that's the top of the screen. So it's 2, 3, 4, 5, 6, 32 is this. So let's just make sure that this all lines up before we start going crazy adding the data in to the PPU. So what we want to do is we want to say, ooh, actually, there's something I just realized that. Oh, okay, good. So I was thinking about, how the memory is arranged where like this is at 2800, but if you're doing the mirroring in a way where you're more vertical like we do with cerulean ascension, then you have to jump over this part of the name table address space. But in this case, because we're doing um, vertical mirroring, we're dealing with just these horizontal name tables, so it's just a contiguous array of bytes that we're manipulating. So I can just easily say we want to write to 2000, which is the top left corner here. And we have 64 bytes times 2 rows, that's 128 bytes, and it's a name table. So once the emulator closes, we will. Oh, it's not exactly the most comfortable place to be sitting. It's pretty cool. It's like a stair step area in the convention center. One error found. Name table. What did I do? What did I do? Did I not declare it as an extern? I did not. Extern const unsigned character name table array. Okay, let's try that again. There we go. All right, so let's run that. All right, so oh, you know what? I know what I did wrong, but okay, that was kind of dumb. All right, so I'm thinking we're going to linearly. It's just a thing of like because of the visual layout of it here, I didn't really think about what the address space actually is. So I'm thinking we're going to linearly address across this memory like this, forgetting that this is 2400 hex, this is 2000 hex. So what we're really doing is we're filling up this name table, and then we're going and filling up this name table. So what I really need to do is not this. I need half as many of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let's get rid of the first 16 here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So get rid of these here too. So that's how, looking at things visually, it's so powerful because like it can totally change the way your brain is thinking about the data versus what the reality of the situation is, right? Because it's not actually arranged linearly across these memory spaces, but not thinking about it, my brain was like, well, of course it's there, because why wouldn't it be? And the answer is because that's not how that memory works. So let's see. Let's just do this kind of different way because it'll be a little bit easier. So I want to change these to 0. So place, yeah, let's do that. Just as a little bit of a headache savings for myself. Oops. Even if I mess it up, it's not really a huge deal to fix that. So, we want to make sure that there isn't one on the right-hand side here because, like, when we fill that in, it's going to be open on the right-hand side because we're scrolling from left to right and right to left. You'll see what I mean in a second. The other thing I'm doing that I haven't done in a while is I have Twitch recording this, and making this available after the stream is done. So hopefully the quality is pretty good, and that means that folks will be able to go back to this and look at what we put together here, and it's intelligible. Usually at home, what I do is, because I have more storage and it's a more powerful system, I'll record locally, because I know then you're not losing anything to, like, the internet glitches out for a moment, and you get some sort of corruption on the stream. But just because I'm limited and using my MacBook here, I figured we'll just have to hope that that works and it's good enough. Nobody's complained about the quality of the stream so far, so I can't imagine that it's too bad. All right, so we're off a little bit. It looks like we've got one extra byte somewhere. I'm just going to be kind of lazy about this and use it to a visual way of seeing this, to just kind of see what's going on with the stuff we're loading in. One thing that might actually be useful is let me actually set this to 25, just so I can see where that data ends. So is this the emulator doing something weird with, like, cropping, or what's going on? Because this looks weird. Is this just a aspect ratio issue? Because that does not look like does not look like what I was expecting it to look like. Yeah, so it's just okay. All right, good. So we can set that back to 0, and then what we're going to do is just kind of paste in a bunch of these and try and populate just the first name table. And so what is that? That's 32 by 30. It's 960. I don't know if that's going to work. I don't know if it's only accepting a byte for the parameter. Yeah. All right. So that's fine. So what we're going to have to do is we're going to have to say 255, and then I don't know if this is going to work either, but we'll see. 960 minus 255. Actually, yeah, so that's still not enough. Five ten 960 minus. Oops. Really? I have to do this a couple times. I don't know if this is going to let me do this, actually. 765. We'll see in a second. So this is one of the downsides of using the C code, is like you run into these limitations because of the underlying compiler. It's not the compiler's fault. It's like the limitation of the system, right? Like, this is expecting a byte to be passed in because that's all it can do. So then that's fine, right? But then that, like, you run into, yeah, that's what I thought. You run into this weirdness of, like, you've got to do it in multiple pushes. Actually, so this also raises the fact that I've got to do this at here. Geez, what a pain. So like in our assembler code, if we're loading the name table with all this data, we write some loops to handle it. But because we're doing, I guess we could do that here too. Let's see if we can do that here. I kind of don't like the way this looks for the name table. Not only that, it's just like really sloppy. Um, let's access the registers directly and see if we can do the same thing. So we need this NES.h, which defines those constants for us. And what we want to do is we want to say PPU address, right? Is that what it is? PPU address is equal to OX20, and then PPU address is equal to OX00, right? So we're doing the same thing we would do in assembly. We would say, okay, set the address register with the high and the low bytes, and now we're going to write a loop where we actually write the data in on the 2007 register. But instead of doing it in I'm going to make an integer global for looping because it's going to be a 16-bit value, and I don't want to be messing with the stack for that. So I is 0, I is less than 960. We're going to increment I, and we're going to say name table, actually PPU data is equal to name table I. Right, so we're just looping through the name table, and byte by byte, we're setting the PPU data. This is, again, what we would normally do in the assembler, but instead of doing it this way, we'd be juggling registers or temporary variables or something like that. So I think this will work. Let's see. 76 in line 37, identifier. Oh, I have an extra close parentheses. All right, we'll see if this works. I don't know. We may have to mess around with it a little bit. Okay, so that seems to have worked. That's not half bad. Let's keep going. So one of the things that we're doing that isn't good is we're reading past the length of this data. It doesn't really break anything, but it's also not great because you never want to do that anyway. But you can see we're getting what we want, where it's actually filling out more and more. These tiles here, that's the palette data. Not no, whatever comes after. It's the ship sprite data. It's just happening to get read because we are telling it to read more data than we actually have. Again, like I would never do this or I shouldn't say that. This is not the optimal way of doing this, right? Because I'm just hard coding these values into the ROM. But for the purposes of, I don't know if I actually compiled that last time. For the purposes of what we're trying to do here, it's just kind of quick and dirty to get things kind of bootstrapped. This is an easy way to do it. All right, so I think we're just like at the edge of the name table. So let's add 2 more and let's see. So that's been the sort of surprising thing for me for using C on the NES is just like how much simpler and more straightforward some of this stuff has become. Oh, you know what? So, okay, so there's 2 parts to this that I didn't think about. And FCEUX is buggy on the Mac. I miss messing. So 960 is just the one name table, but there's also the remaining bytes that set the name table attributes that we don't want to mess with. I have no interest in in doing anything related to attributes right now. So we need to do two 960 byte loops to set both of those name tables on startup. Oh, I got it right. So if you look, I'm actually off by one row. I guess there's some cropping going on. All right, so this is that. So what we really want to do is we're going to copy this row and replace this one with the same one from the top. We have the stuff all the way across. So we still have emulator. What are you doing this to me? Video config. What is the last line? The resolution is 256 by what? 240? Yeah, 240. Give me the whole damn thing, please. Last line, 239. Okay. But can you? Why are you doing this? Just give me an aspect ratio that doesn't look disgusting, please. All right. All right, cool. So we've got this name table populated. And then what we need is the opposite part of the name table. And let's see. Should we just do the same loop and have an offset into name table, or should we create a new? Let's just create an offset, and this way we don't have to create another. You know what? Let's just do two of them. This way, it's a little bit clearer what these are, and it's not really a big deal to have to do that anyway. So all I'm going to do now is I'm going to do a multi-line select and modify these to be zeros, and I incorrectly modified this, but that's fine. We'll go back and fix that. So now name table 2 is going to have the 25s on this side. Hey Brandon, how's it going? All right, so now we've got our two name tables set up. Let's make sure that that's defined here in this extern. So we've got that. So we've got this loop here. And we've got this loop here, and this is going to be at 2400. Right, and we're going to store name table 2 into that. Let's put some comments here. Update the name tables, starting with X2000, and then populating X2400. Ignore the attribute portion of the name table. Copy the data from name table and name table 2. Right, so that's what we're doing there. Label name table redefined. Did I not change it here? I did not. All right. So what we should see in the name table now is, yeah, perfect. So we've got a green border around the whole name table. And what I want to do now is I want to essentially create almost like a camera system where we follow the sprite around and move the X and Y scroll accordingly. So we don't care about the Y scroll because we're only moving horizontally along the name table. So really what we want to just do is we want to have the camera scroll position being tracked based on whatever the player sprite positioning is. So what we can do is, while we're in here, we can do I think it's ln scroll is the register. Let's see. Oh no, it's actually a function. So we're going to set the X and Y offset based on the camera offset. right? Camera X, camera Y. So nothing is going to happen. You know, let's do something fun. Let's do that with every increment. We're going to, with every frame, we're going to increment the camera X. Oh, what did I break? Oh, type def. Okay, so you can't really see it because there's not much. Okay, there you go. You can see it now. But if you look at the name table, you can see that we're scrolling with the X register across the name table. So now what we want to do, now that we know that that's how that works and everything is looking good, we want to make the camera follow the player. So the player has a position that should be adjusted based on the camera position. And so if the player, I'm trying to think what the best way. So like if we use the example of this window here on the screen, being sort of our region. I mean, it might be a little bit smaller. Like we'd say, like this is the region where the player should be able to move, where the camera doesn't necessarily follow. We might want to tighten that up a little bit. But let's say, you know, if the player's position on screen gets past a certain position on either side, actually, like I said, it doesn't matter the Y position. So again, you know, visualizing that this is the NES screen and this is one boundary and that's another. If the player's X coordinate gets past this on screen, then we want to adjust the camera to fix that problem, right? So what we would want to do is we want to say, actually want to let's we can do something like do a delta X and a delta Y. I keep writing unsinged instead of unsigned. I don't know why. So that gives us what we were calculating here. And that tells us where on screen the player actually is. Because if the camera has scrolled to the right, the sprite should be moved over to the left. So what we want to do is we want to say, all right, so if the player's X position, so if dx is greater than, I don't know, so that's 256. Here, let's use A-Sprite as like a point of reference here because I really don't know. 256 by 240. So let's say if the player is like beyond, what is that X coordinate? 175, greater than 175. Camera X plus plus, and then dx minus minus, right? So we're incrementing the camera position, so that naturally would mean that the player sprite gets moved in the opposite direction. We don't need to recalculate that. We just know that that's what would need to happen. And then if dx is less than, say, 73 or so, like these are all just super rough. We need to go back and refine these to make sure that they all actually make sense. Camera X minus minus and dx plus plus. Who knows if this is right? I would say, and also dx is greater than or equal to 0, right? Because if it's zero, then you're at the left-hand corner of the screen, which means, I mean, that's not the only thing it can mean, but like for now, that's what that means. And so we don't want to mess with shifting the camera if that were to happen. And same thing here. It's like if it's this NDX is less than 239. That might be totally wrong, but I don't know. We'll see as we mess with that. Comparison is redundant. Yeah, I guess so. I guess you're right. Okay, so we sort of got it. I'm sure there's just something goofy in the logic that I was not thinking about. But the basic idea is working. So as the ship moves, the camera is scrolling. One thing we want to do is if camera X does not equal 0, and then if camera X does not equal, what is it? It's 239 minus, so whatever is it 240? Yeah, it'd just be 240. If the camera gets 240, then we've hit the edge of the screen. I think that's right. So we don't want it to, because what's happening is the camera is overflowing into the next name table, which is not what we want. I also want the ship position to not be 0, 0 when we start. So let's fix that. So player.x is equal to, say, 100. Player.y is equal to 100. Good. So no scrolling there. But then if we scroll this way, the camera follows. So we get to the edge, it should stop. Okay, we're a little bit short. Are we just like 8 pixels short? Did I mess up the math there? Probably. That's what it looks like. So it's like it should be 248. Oops. Helps if you rebuild the code. All right, so folks who are here watching, is this looking okay? Going well? I'm gonna need to take a bio break here in a minute and come back onto the stream, but only if this is interesting and useful. Certainly don't want to stream if you don't think this is benefiting you at all. But I'm enjoying being able to see how this is all kind of working with C and how this is almost a very, very straightforward process compared to, how the assembly goes sometimes. So why? Oh, because it's 256, dummy. That's why. Not 240. That's the bottom. There we go. All right. So here in, what is this? Almost 2 hours, as I've explained, we've got a sprite moving, we've got a name table populated with some tiles, we've got the scrolling happening where it's following the sprite. So like this is the basic setup, right? This is like our core of what this would look like. And now what we would want to do, I think, is assuming again that this is something that you all want to continue to see and you're finding this useful. After I take a quick bio stop, I'll come back and we'll start implementing sort of the physics around how to control the boat. So the idea would be that instead of just left, right, and up and down, you'd have left and right to control essentially the rudder direction or the motor direction, and then you'd have I don't know if you'd use up and down to control forward or reverse, or A and B to increase the forward thrust, and B to decrease the forward thrust, or ultimately put it into reverse. Like if you've ever been on a railboat, the controls are very much like that. There's a steering wheel that controls the direction of the motor. Well, it depends on the boat, but like on boats that I've been on, there's a steering wheel that controls the direction of the motor, and then there is a throttle where pushing it forward increases the power in the forward direction, and there's some level of control there, and then if you pull it back all the way, there is reverse power as well. So, so that's what I'm thinking I want to try and implement now. The next part after that would be like, how does the water affect that? But, one step at a time. So, what do you all think? Should we come back to that? I'm looking for some responses on the chat. Should we come back to that? Is this a good enough sampler? You're all satisfied with C and what that looks like, to how that comes together? Because I definitely need to take a quick break. And I have to end the stream to take the quick break because I'm not leaving my equipment just plugged in here and streaming in the middle of the convention center. And my headphones are at about 50%, so I can pop them into the charger and get a little bit more battery life on them. Anybody? Have I put you all to sleep? All right. Well, nobody's threatening to report me on Twitch, so I'm going to assume that maybe this is useful. Let's see. Yeah, everything is still going. So what I'm going to do is I'm going to stop the stream here for a few minutes, take a quick bio break, and then I will start again, and we'll do some of the control stuff. We can play around with that, and in particular, what I'm hoping that'll highlight is how much easier it is to work with values both positive and negative in C versus assembly. Some of you may recall some of the work we were doing with math early on in the code for cerulean ascension, and what a pain that was. So I'll see you all in a few minutes. I'll restart the stream soon, and talk to you in a moment.